So after the forward and reverse bias, within again in the reverse bias, there is a term which is called reverse breakdown. What happens if we increase the reverse bias voltage to a very large enough value, which the diode could not sustain? So there will be a breakdown. And in this condition, what happens? Let's try to understand. So assume that there is one minority conduction band electron which acquires enough energy from the external source to accelerate towards the positive end of the diode. Now, during its travel, it will collide, of course, with another atom, and it will impart enough energy to knock a valence electron into the conduction band. And the result will be that now there are two conduction band electrons. Similarly, each will collide with an atom, knocking two more valence electrons into conduction band, and now there are four conduction band electrons. And in turn, they will knock four more electrons into the conduction band. This rapid multiplication of conduction band electrons, it's known as avalanche effect, and it will result in a rapid buildup of reverse current. However, in reverse bias, the current usually don't flow, but in case of breakdown, there is the flow of current, and that is not the normal scenario. It's the abnormal scenario. So most diodes, they are not normally operated in reverse breakdown, and of course they are damaged in case of the reverse breakdown because the voltage is too high. However, a particular type of diode which is known as Zener diode is specifically or especially designed for reverse breakdown operation. So if we summarize, if reverse voltage goes beyond the limit, depletion region will break or it will be overcome, and in result there will be breakdown. There are two types. One is avalanche breakdown, which we have just discussed, and when we will discuss a special type of diode, we will also see what is Zener breakdown. So in this, current increases rapidly, and usually after reverse breakdown, the diode is damaged. So then the diode is no more a diode. Now we are going to discuss the diode characteristics, that how it acts in forward, how it acts in reverse, what is its application. So starting with, so far we have discussed that diode is a semiconductive device with a single p-n junction, and it conducts current when it is forward biased and when that bias voltage exceeds barrier potential, and it prevents or blocks the current when it is reverse biased at less than breakdown voltage. More than breakdown voltage, there is reverse breakdown, so also current flows in reverse direction, but the diode is damaged. So this section we are targeting the basic diode characteristics. We will try to explain the diode via characteristics curve. We will be able to recognize standard diode model or symbol. Testing the diode with ohmmeter, we will cover this in our lab, and we will discuss finally three diode approximations which are used for circuit analysis. So these are the characteristics of a diode. Here VF shows forward voltage, IF shows forward current, VR means reverse voltage, and IR means reverse. So this portion is forward bias portion, this portion is reverse bias portion, and this is for the silicon. So we know till 0.7 volt there is no flow of current in forward bias. After 0.7 volt, barrier is broken and there will be flow of current in the forward bias region or direction. However, in reverse bias, there is no any flow of current less than the breakdown voltage. But after breakdown voltage, there is again the flow of current in reverse direction, and that is not desired. Okay, so these are general diode VI characteristics. As far as diode symbol is concerned, till now we have seen the diode structure, which is this one: P region, N region, PN junction. These are the metal contacts and wire leads. This is diode symbol, and this symbol has also a meaning. This arrow shows that from anode to cathode, this allows the current, and from cathode to anode, this line shows that it blocks the current. So anode A, cathode K. When anode is positive, cathode is negative, forward bias, it allows the current as per this arrow from left to right. If cathode is supplied with positive, anode is supplied with negative, that is reverse bias. So this line shows it blocks the current in reverse bias. Now, how we identify the diode in hardware setups. So these all are the uh, diode packages as well as their terminal identifications. A is anode, K is cathode. From these varieties, we will use this one in our lab. And how to identify the anode and cathode? So this is a line, a white or silver color line on the end. That end shows the cathode, so automatically the other end is anode. And when we will perform this lab in hardware, so we will use this type of diode. Now let's see the diode approximations, and within them we have three models. We are starting with the ideal diode model. Then we will discuss the practical diode model, and finally the complete diode model. And we will again summarize them with their usage or applications. So the ideal diode model is very easy. In forward bias, this is a circuit, supply voltage, a resistor for limiting the current, and a diode. So in case of forward bias, this diode acts as a switch and the switch is on. No any voltage drop. In reverse bias, no flow of current, current zero. So we say switch is off. Okay. In forward bias, switch is on, our circuit is closed. In reverse bias, switch is open, our circuit is open, our switch is off. So here, from here we get the application of the diode, that diode acts as a switch. This is the application of a diode. However, the switches that we used in our normal life, they are mechanically operated switches. We change their position with our hand, with our fingers movement. We change their position, their status of on and off. However, this is electronically operated switch or voltage operated switch. As after 0.7 volt, if the diode is made of silicon, so that will be on. Before 0.7 volt or less than 0.7 volt, that will act as off. Okay. So these are the characteristics of this ideal diode model, that in forward switch is on, so there is flow of current, no voltage drop. In reverse, because the switch is off, so it blocks the voltage and no flow of current. So this red line shows the characteristics of diode in perspective of the ideal model. Now let's come to the practical model. We know practically there is some voltage drop across the diode, that is 0.3 volt for germanium, 0.7 volt for silicon, So how to represent that drop? Again, this is input or bias voltage resistor. This is now complete practical diode model. Now again a switch that we used in our ideal model, and that switch is now added with a battery VB showing the barrier potential, and this shows the drop which is practically uh, uh, considered. So now this complete is the practical diode model: a drop, a voltage drop due to the barrier or barrier potential, and a switch. However, in reverse, this is same just like the ideal, because in reverse the switch is off, so there is no drop because the flow of current is zero. So if we now draw its characteristics, in reverse they are same. Only in forward bias it conducts after 0.7 volt. Before 0.7 volt, no flow of current. After 0.7 volt, current will flow. However, the complete diode model is more accurate. Uh, Now the same drop, the same switch, and a resistance which is called small forward dynamic resistance. And that is basically the part of the actual diode, because in actual diode there is some variation in the voltage drop due to the flow of current. So that is represented by this small resistance or small forward dynamic resistance. Now in reverse bias this is same, only a resistance in parallel which shows a very small leakage current. So the value of this reverse resistance is very high or large. And if we plot its characteristics, so now after 0.7 volt in forward, there is a slope due to the low forward resistance. However, in reverse, there is a very small leakage current due to the high reverse resistance, and this is more feasible in terms of the actual diode. However, we must focus on the scale. In forward direction, current is in milliampere. In reverse direction, current is small and the unit is microampere. Okay, so let's summarize. Diode approximations actually simplify the behavior of a diode so that we can analyze circuits without complex equations. The first approximation is ideal diode. Of course, in this diode acts as a very perfect switch. So in forward bias, this is just like short circuit, zero voltage drop. In reverse, this is open circuit, no current. The key point is that voltage drop is zero, and of course this is ideal, not real one. So the use is only for basic understanding and for quick circuit analysis. From accuracy point of view, this is less accurate. The second approximation is practical diode. Now diode has a constant voltage drop. That constant voltage drop is 0.3 volt for germanium, 0.7 volt for silicon. Typical values are as we discussed. So forward bias conducts with that fixed voltage drop, that is this one. In reverse open circuit, no flow of current. So that equation is voltage drop 0.7 volt approximately for silicon, and this is most used in practical problems. However, in actual, more accurate is complete model. So this has very high accuracy. Ideal model was less accurate. The practical model is bit more accurate. However, the highest accuracy is with the complete model. So diode has some threshold voltage that is again same, 0.3 volt for germanium, 0.7 volt for silicon. But now there is some internal resistance which is small in value, so that varies the drop across the diode, and that equation is given by this, the threshold voltage and some drop due to the dynamic resistance. So this is threshold voltage, this is dynamic resistance, and this is the diode current. So this is more accurate than all previous models. And with this, we conclude this session with this quote. Hopefully, from this quote, you will inspire